Hello everyone. Today I'm going to present a paper titled Deep Learning-Based Scene Simplification for Bionic Vision. In the world, up to 200 million people have visual impairment because of retinal degenerative diseases. In recent years, a lot of retinal prostheses have been developed in the hope of restoring their vision. And here is an overview of a retinal prosthesis. The patient has a retinal implant, which is an electrode array tacked to the retina. When the patient wears the device, the camera will be capturing all the visual information in the front and translate that pixel intensity to stimulate the electrode and thus producing prosthetic vision. However, the current retinal prostheses are still rudimentary because of limited resolutions of electrode array and also the distortions due to interactions with the retina. Here is an example of a busy train station. In the bottom, this is a simulation of what a patient will actually see. And you can see a lot of details are missing. So the current devices are of very limited use for daily activities. In this paper, we use state-of-art deep learning-based scene simplification strategies in order to maximize the usefulness of bionic vision. In addition, we use a psychophysically validated computational model of the retina to generate more realistic simulated prosthetic vision. In the experiment, we use 4 different scene simplification strategies. Number 1 is highlighting visually salient information such as the regions with high contrast or high brightness. Number 2 is substituting depth for intensity so that the regions that are closer to us have higher intensity values. Number 3 is segmenting important objects from the scene. And number 4 is a combination of all 3. We took the top 10% regions in saliency map and then we combined with the segmentation mask. Then we scale the pixel value based on the depth information so that the objects that are closer to us have higher intensity values. In order to produce simulated prosthetic vision, we used a model called PosttoPercept. In most of the literatures, people usually use pixel model to produce simulated prosthetic vision. What that means is they assume that if you stimulate one single electrode, you will actually see a very localized phosphene. However, that's not the case. Evidence have shown that the percept shape is actually aligned with the axon fiber trajectories in the retina. So here is what the phosphene will actually look like. The PosttoPercept model is able to parameterize the shape using 2 parameters, rho for the phosphene size, lambda for the phosphene elongation. Here we used 9 combinations of different model parameters and also 3 electrode array resolutions. These are the examples from before. So if you assume a pixel model, you will actually stop right there. And then what we did is we actually passed those images into PosttoPercept and produced more realistic simulated prosthetic vision. You can see a big difference here. In the experiment, we used 16 first-person outdoor videos recorded at UCSB. 4 of them have no people, no cars. 4 have only cars. 4 have only people. 4 have both. We recruited 45 sighted undergrad students. We asked them to watch simulated prosthetic videos online and answer some questions about the presence of people and cars. Then we measure their performance using D', which is a measurement of perceptual sensitivity calculated from the hit rate and false discovery rate. So higher D' means better ability to detect the presence or absence of people and cars. Here we found that segmentation has the most significant effect for improving performance in recognition tasks. Combination is also very good. However, it's not necessarily better than just using segmentation alone. We found that smaller phosphene sizes yield better perceptual performance. However, we did not find a significant effect for elongation parameter. However, if we plot all 9 parameter models together, you can see a clear decreasing trend as we increasing phosphene size and elongation. We found that higher electrode array resolution yields better perceptual performance, but it plateaus at 16 by 16. If you increasing even more, there is no benefit. In conclusion, we found that object segmentation best supports scene understanding. However, saliency and depth information may be more useful in other tasks. We also found that increased percept size impedes scene understanding, and it is very important to use biologically realistic phosphine models such as PosttoPercept to produce simulated prosthetic vision. It could also allow us to model individual differences by changing the parameters of rho and lambda. We also found that increasing number of electrodes does not necessarily improve scene understanding. It plateaus at 16 by 16. It might be more important to reduce distortions. In the future, we'd like to study our scene simplification strategies in other tasks in immersive VR environment, such as open-ended navigation. Our ultimate goal is use end-to-end training of scene simplification strategies fit to an individual patient. I'd like to thank all our colleagues who have helped our project and also National Institutes of Health for support. Thank you for your time.